In class, welcome. I'm sorry, I really tried to get you, but I don't know what was happening. I was not able to get the class rep. So we will start because I think we should be starting at 9. So last time I welcome you to this morning's class, and I hope you are ready for the class. So we are done with the narcotic analgesics, and I hope, in fact, also, I don't know when you are handing in your assignment. I don't know whether it's your class I'm picking on Monday. But if it could be ready, the earlier the better. So we are done with the narcotic analgesics, and even I think the last group we discussed was the antagonists, and now we are starting on a new, as I say, the topic should be narcotic analgesics and others, and other CNS drugs, and of course also some are not really CNS drugs. So we are starting with a new subtopic, and we'll be looking at the anti-Parkinsonian drugs. So this is not as wide as what we have looked. We have already done in the subtopic narcotic analgesics. So we should be able to finish pretty early. So we start with the anti-Parkinsonian drugs. So can you tell me, what is Parkinsonism? Have you heard of Parkinsonism? What is Parkinsonism? Have heard of it? Yes or no? Parkinsonism. Heard of it on yes or no? Have you covered it in pharmacology by any chance? Yes or no? Parkinsonism. Have you covered it? Or the Parkinson's disease? Have you covered it in pharmacology? No. Okay, fine. Then we can. Then we'll do it together. So when we look at our minds or our brains, we have several neurotransmitters. And for proper and optimal functioning of our bodies, all those neurotransmitters should attain a certain balance. Because if you have excess of one, you will have particular deficient problems. So you should always have a balance of all the neurotransmitters. We have transmitters like acetylcholine, dopamine, we have serotonin, we have GABA. All these are neurotransmitters that are in the brain, and they are very, very important in the transmission of information, because you remember that the information, most of the information that we get, or which we get in our periphery, comes actually from the brain. And therefore you require those neurotransmitters. They are chemicals that bridge the gap. You know, you do have the gap where you have the neuron where the neuron is touching the cells. You do have a gap, and that gap requires that chemical to move, to transverse in between, to actually transfer the information that is found or that has been conducted by the nerves. The information will come to the nerves and then get to the end, where the end of the nerve, and at the end of the nerve you have a gap, and that gap you require, or the presynaptic gap, that gap you require the neurotransmitter to get into that gap, to transfer the information over, so that the information can continue and the information is processed to a particular action. So now you do require the various transmitters to be in balance. If they are not in balance, you will have conditions like you will have somebody perhaps has psychotic problems. And for Parkinsonism, it is where you have two neurotransmitters. You have dopamine and you have acetylcholine, and these two are supposed to be in balance. They are the ones they are the two neurotransmitters that control movement, and also a bit of thinking. So once these two neurotransmitters are not in balance, then especially if the dopamine is in lower concentrations than the acetylcholine, then you will get the condition we call Parkinson's disease. So Parkinson's disease is when you have a condition, could be the neurotransmitters, the cells that form dopamine have a problem, and once they have degenerated. Once they have degenerated, they fail to produce your dopamine, your acetylcholine levels might just be normal. But since the dopamine levels have gone down, it will be like there's an imbalance between dopamine and acetylcholine. And once that happens, you will have Parkinson's disease. Once the degeneration starts, it's very difficult to reverse it. So that's why you find that this disease will continue progressing, but you will be able to control the symptoms. The symptoms or the problems in movement, because you will have rigidity, you will have the person falling over, they cannot stand straight and so on, and uncoordinated movement. You can't be able to control that, the symptoms, but unfortunately, the disease will continue on and on once the dopamine neurons start degenerating. And therefore, for the management of Parkinson's disease, we are managing the symptoms. We cannot cure the disease, because we cannot be able to bring back the nerves, all the neurons that have already degenerated. So in short, that is our disease, Parkinson's disease. We will look at the various drugs that can be used in the management of Parkinson's disease. Just sing like just 1 minute. More recent PPT presentation, I'd actually loaded the wood down. Sorry about that. But we started about, we can say we are starting about 10, so we'll give ourselves 2 hours. So as I'd already said, is that we do require a balance of neurotransmitters in our brain if we are going to work optimally. And when we have either excesses or deficiencies, of course, we have also serotonin deficiencies or excesses of some of those neurotransmitters, we have CNS conditions. And indeed, you will study quite a number of them. So let us look at the definition. And we can say Parkinson's disease is a degenerative disorder of the CNS dopaminergic neurons, which shows it should have, which has mainly motor and sometimes cognition or thinking-related symptoms. So you can see it's degenerative. It is on the dopamine receptors. And that's why we have said once it starts, unfortunately, it just progresses. But you can, it has very severe or very debilitating symptoms, and therefore you can't stop the symptoms, and the person, especially at the beginning, the person might still be able to live a normal life. Movement, so you have movement-related motor, shaking, you have rigidity, you have slowness of movement, and difficulty with walking. So those are some of the issues that you have. The person is shaking, they are rigid, they have slowness of movement. You look at those, you categorize those movement defects into 4 categories as we move on. Then there's the cognitive problems, especially dementia. That occurs mainly at the end as the disease continues to develop. Then you find that even the acetylcholine levels are affected, and therefore you do have the cognitive problems. Parkinsonism is a clinical syndrome with 4 cardinal features. 4 cardinal features, and you will have bradykinesia, and bradykinesia is slowness and poverty of movement. You have muscular rigidity, you have resting tremor, which usually are based during voluntary movement, and you have an impairment of postural balance, leading to disturbance of gait and to falling. You might just find the person falling. The person has, as we have said, muscular rigidity. They have tremors. Sometimes I believe we have seen people, even when you go to give, trying to give them a cup of tea, and their hands are really shaking and they cannot. Some of them, of course, is because of withdrawal symptoms of alcohol, but some of them could be because of Parkinsonism, of Parkinson's disease. Of course, named Parkinson after the person who is supposedly discovered this disease. So we are looking at quite a disease with very terrible, with quite severe symptoms, because you have an influence of movement. And when you cannot move, you are rigid, you can't move, you fall. They will also have a lot, they will wear also your confidence, and you'll be most of these people are very, very withdrawn. Therapeutic goal, and as I have said, it is symptomatic relief through restoration of balance between the neurotransmission by acetylcholine and dopamine in the basal ganglia. So it is symptomatic relief. It is not treatment. Drugs do not treat the condition, but they can be able to manage it. Acetylcholine, a chemical messenger involved in memory, judgment, and learning traits, which are lost in dementia state of Parkinsonism, which only occurs sometimes at a later stage. So when again, as the disease progresses, you can, as I have said, you can also have a low levels of the acetylcholine. Initially, you start as an imbalance of acetylcholine and dopamine, where the dopamine levels seem to be low. But as the disease progresses, you can also have dementia, because again, you can also have low concentrations of acetylcholine. And if that does happen, you can see acetylcholine is important in memory, in judgment, in learning, and therefore you can have that side effect. And at that particular time, you can give drugs which will increase the levels of acetylcholine. But as again we have said, you cannot go back. It is a disease that whereby we can only treat the symptoms. Parkinson's disease is caused by an imbalance of dopamine and acetylcholine. Acetylcholine and dopamine need to be balanced for smooth movement. So these two neurotransmitters must be balanced if we are going to have smooth movement. Dopamine causes muscle relaxation, whereas acetylcholine causes contraction. So if you have reduction of dopamine in the basal ganglia, it will result in an imbalance of the relaxation, muscle relaxation, and the contraction. So if you have an imbalance of muscle relaxation and contraction, because the dopamine is the one which is controlling the relaxation, so you have more contraction than relaxation. So that means you will not, of course, have balanced movement. And that's why we are saying you will fall, you will have rigidity, and all those complexity. In some cases, at later stages of the disease, reduction of acetylcholine, which is also involved in learning and attention, leads to dementia, as we have already said. And this is just an illustration or schematic representation of the imbalance. So we are saying when the person is normal, you are at this level there, where both the levels of dopamine and the levels of acetylcholine are the same. Now, when you have an imbalance, it will be like there is, of course, the balance, there is a tilt such that the levels of acetylcholine are much, much higher than the levels of dopamine. In other words, you have dopamine deficiency of that level there, and you have acetylcholine excess of that amount. And when you have that imbalance, then you will have a patient who will have those symptoms of Parkinsonism. So again, very important for these neurotransmitters to be balanced, to give us a balance of movement. Now, that is just an introduction. I want to believe that when you look at it in pharmacology, you will be able to study more of the disease. But our mind is mainly to look at the drugs. But it's good to have an idea of what this disease is, and also to understand that even as we look at the drugs, we are only managing the symptoms, so that we try and give the patient quality life. But ultimately, the disease will finally, of course, it will finally kill the patient, because the dopamine, the nerves, the neurons, the dopamine neurons, the dopaminergic neurons will continue degenerating until, of course, the last moment. So let us look at the classification of the drugs, and we have several drugs. We have several drugs that have been developed for management, as we have said, of Parkinson's disease. And we can start with the first category, which is a cholinergic therapy. So the first category is cholinergic therapy, and under the cholinergic therapy, remember we are saying is the acetylcholine levels which are high. So although we are calling cholinergic therapy, it should be giving drugs that reduce the acetylcholine level. So we have the anticholinergic drugs, we have menstropin, benzhexol, and these ones will reduce the acetylcholine effect. Treatment for tremors in early stages. So that is of importance. Anticholinergic drugs. And you can also have the cholinesterase inhibitors. Remember, we have said when the disease progresses to dementia, then you have issues of acetylcholine. So you can use cholinesterase inhibitors like rivastigmine. Rivastigmine is a cholinesterase inhibitor. It will decrease the rate of metabolism of acetylcholine, and therefore increase the levels of acetylcholine, and hence that is only used for management or management of the dementia in later stages. Then you have the dopaminergic therapy, And here is where now we are trying to increase the activity of dopamine, either by using agonists, either by increasing the amounts and so on. And we can have the dopaminergic therapy, and we can start with dopamine releasing agents, whereby these drugs will get into the body, use the transport system of dopamine, get into the vesicles that store dopamine, and release the dopamine. So you can see, of course, that kind of treatment or management has a shortfall, because if you do not have any dopamine in the vesicles, there's nothing to be released. But that is being called dopamine releasing agents. And in that category, we have amantadine, and then you have dopamine replacement, whereby we give compounds that can be in the body change to dopamine. And of course, we have the prodrugs like levodopa. And of course, we will find that the levodopa, if you give it on its own, it has some challenges. It will be metabolized through decarboxylation in the periphery to dopamine, and it will not get into the brain. So normally we give the levodopa in combination with the dopamine decarboxylase inhibitor. So we do not give the dopamine decarboxylase inhibitor alone. We give it with the dopamine prodrug levodopa. The idea is that you want to retain the dopamine for it to, the L-dopa, for it to penetrate the BBB, to get into the brain before it's converted to dopamine. Because if it's converted to dopamine, the periphery, for one, you will have a lot of toxicity. Two, you will not get it into the brain, because dopamine does not cross the BBB easily because of its water solubility. So you give it in combination, and when you give it in combination, some of it may be undergo degradation, but you will get a higher percentage of the L-dopa getting into the brain. And then in the brain, the L-dopa will be converted to dopamine. The advantage is, as you see, the carbidopa, which is the decarboxylase, does not cross the BBB, and therefore is left in the periphery. So it inhibits periphery metabolic degradation of dopamine. Then you have the dopamine receptor agonists. And these ones are drugs that you can give. They sit on the receptor and they elicit, they bring about the same effects as dopamine, and therefore help in control of the symptoms. So you can have those which are agoline derivatives like bromocriptine, and you can have the non-agoline derivatives like clopidogrel and pramipexole. These are the ones that do not have the agoline structure. The agoline is quite a complex structure, and all they do is promote dopamine effect in the brain. We look at them one by one. Okay, what does happen? Then we have now metabolic protective agents. Dopamine is rapidly metabolized in the brain. You have the catechol-methyltransferase, you have the monoamine oxidases, which rapidly metabolize, and of course, you have the dopa decarboxylase. These are enzymes that rapidly metabolize dopamine. So you can inhibit these enzymes. If you inhibit the enzymes, that will imply that the metabolism of dopamine will be slowed down. And once it's slowed down, the concentration of dopamine will come up. So that's what we're calling metabolic protective agents. We've already mentioned one, the carbidopa, where we are talking about aromatic L-amino acid decarboxylase inhibitors. We have the carbidopa, reduces the decarboxylation of L-dopa in the periphery, not in the brain, because it does not cross the BBB. Then you have the monoamine oxidase B. Remember, we have monoamine oxidase A and B. B is more concentrated in the brain. A is in the periphery. So again, you will look for selective inhibitors that will go for B, not A. Because if they go for A, they can bring us a lot of toxicity, as we're going to see. So you look for selective inhibitors of monoamine oxidase B, and means they will inhibit the oxidation of dopamine. And we have an example of selegiline, which we look at, inhibits the metabolism of dopamine in the brain. Then, of course, also another metabolic pathway of dopamine is a methylation of one of the catechol-hydroxyl groups. And therefore, you can also have drugs that can block the catechol-methyltransferase inhibitors, and you have entacapone and we have entacapone and tocapone, and these drugs again will inhibit the metabolism of dopamine. And once they do so, as we have already said, there will be increased concentrations of dopamine. So let us now mention something about the anticholinergic therapy. And when we look at anticholinergic therapy, mainly we are interested in those antagonists for the muscarinic acetylcholine receptors. So the muscarinic acetylcholine receptors are the ones that are responsible for the movement, of course, not the nicotinic. So we are not blocking the nicotinic, we are interested in the muscarinic acetylcholine receptors. So antagonists of muscarinic acetylcholine receptors in the CNS tend to diminish the characteristic tremors of Parkinsonism. And so what are we saying here? We are looking at acetylcholine. Acetylcholine is the agonist for the muscarinic receptors. Now we want to convert acetylcholine to be an antagonist, so that when it will be able to recognize the receptors, sit on the receptors, but not elicit its biological activity. So structure to the relationship, we were very simply, this is very condensed. We are going to look at it. We are going to look at it in an elaborate manner. And we are saying the structural modification of the natural muscarinic acetylcholine receptor ligand, acetylcholine, leads to therapeutically useful anticholinergics. So we are starting with acetylcholine. We must structurally modify it in a manner that it will get to the receptor, bind the receptor and bind it strongly, but not trigger any biological activity. Replacement, like we are going to look at this in details, is just a summary. Replacement of the acetate moiety of acetylcholine with a bulky lipophilic structure. That's one thing you see done. And of course, acetylcholine, when you look at its structure, we will see that it has a quaternary ammonium group or ion of acetylcholine that was also changed to a tertiary amine. So that we'll look at in details just in a minute. Some of the examples of the antimuscarinic derivatives is procyclidine, trihexylphenidine. You can see, you're going to look at the structure. And if you look at acetylcholine, this area here is very simple. This is a hydrogen in acetylcholine. This is a hydrogen. That is also a hydrogen. And then in between here in acetylcholine, you have an ester. So let us just look at acetylcholine. So if you look at this, is the acetylcholine. So you can see this CH3 there. That is CH3. And then you have this ester there. So this ester in that first drug, that has been removed. And then this CH3 has been substituted by bulky groups. And one of the hydrogens has been substituted by hydroxyl group. Everything, of course, and this, which we are saying is a quaternary ammonium ion, as you can see, is made into a tertiary amine. But we'll go through that. But I just wanted you to see, from the beginning, the structural modification that has been done. So if you look at this, as I have said, this is that methyl group, CH3. So one of the hydrogens replaced by hydroxyl group, and then the two other hydrogens are replaced by carbocyclic groups, large groups. And then in this first drug, procyclidine, the ester group is actually removed. Then you can still see you have the two carbon atoms, just like in acetylcholine, and then you can see now your nitrogen there. It is not a quaternary nitrogen, it is a tertiary nitrogen. But of course, in the body, it will be protonated to give us not a quaternary, but of course, the ammonium ion, which of course is also protonated. Then you have also the trihexylphenidine, and if you look at the trihexylphenidine, also very, very similar. Indeed, here the main difference is that instead of the pyridine ring, we have a piperidine ring. So instead of pyridine ring there, we have a piperidine ring. Otherwise, the structure is the same. Just 1 minute, I close the door. So then we have benzitropine. Again, you can see it now here. We don't even have the hydroxyl group. One of the hydrogens, it is retained. You have two aromatic or cyclic aromatic groups. And then now our ester there, you can see it has been replaced by an ether. So we are only looking at these drugs, and you see them. In fact, that is the common principle that we have. Of course, we have this one whereby you change the whole ring. Instead of having the two rings, you have the tricyclic derivatives, and they have also been found to have activity. So those are some of the drugs. It is important to remember some of them, and we can't be able to relate them. We can't be able to relate them with the acetylcholine, and by looking at the structure of acetylcholine and seeing how the groups or the substituents within the acetylcholine have been structurally modified. So when we look at the acetylcholine, we can't be able to name the various portions. So this first portion here is the acetoxy group. Then, of course, that took beta carbon, alpha to the nitrogen, beta to the nitrogen. That is our ethylene bridge. And then, of course, here we have our quaternary methyl ammonium ion, or the quaternary ammonium ion or onium group, which is at that position. So that is our acetylcholine. This is the acetylcholine that is an agonist to the muscarinic receptors. What do we need to do to change it to something or to a drug that is a... And as we have said, so now we are looking at this group, this methyl group, and that carbon is this one. And now we want to look at the general structure of the antagonists. And if we look at the general structure of the antagonists, we can put our carbon R1, R1, R2, R3 on the methyl group. And then we have the ester linkage, which we have said we can change it, or we can change it and still retain activity, or of course, and develop new activity as antagonists. And then we have the R4. So the first group is the acetoxy group. This so the first group, sorry, is not the acetoxy group, but the methyl group. The second group is the ester linkage there. The third group is our ethylene linkage that we have put as R4, and then our oxonium ion, which this time we have not put it as an oxonium ion, we have put it as a tertiary amine. So we can say this is our general structure. And if we look at the trihexyl phenydyl, we can't be able to compare that with that, where we are saying we can say OH there, you can consider that OH is R1. This there is R3. This there is R2. So we have taken care of the whole of that group. The ester is removed. The ethylene group there is still there as our R4. And then our tertiary amine is there as what we have there. So we can't be able to relate the compounds with the structural modification that has been done on the acetylcholine. So we are saying the acetyl methyl group is substituted with at least one phenyl ring for antimuscarinic activity. So it must have at least one phenyl group for antimuscarinic activity. So we are still on the SAL, the anticholinergics, and we are looking first at the methyl group. So SAL of anticholinergics, I've done some of these corrections in the other presentation, but I realized it was lacking. I didn't search well, so that's why I have gotten rid of it. But I've done a bit of corrections, but I hope I'll remember the corrections. So the SAR of the anticholinergics, and of course we are looking at the methyl group, and we have this is just again emphasizing on what I've already said, that one R1 may be a hydrogen atom, it may be a hydroxyl group, it can be a hydroxymethyl group, or a carboxyamide, but most of the ones we look at do have it as a hydroxyl group. But it can be a hydrogen, it can be a hydroxyl group, it can be a hydroxymethyl, that means a CH2OH, or a carboxyamide with retention of activity, but not agonist activity. In fact, with development, change of agonist to antagonist activity. Then R2, R3 should be carbocyclic, meaning carbocyclic or heterocyclic. That means they can be all carbon, or they can even carry a heteroatom with retention of activity. So we can have phenyl, we can have cyclohexyl, we can have cyclopentyl for maximum antagonistic activity. Most of the drugs that we look at actually have the the carbocyclic group, but we are saying you can also have a heterocyclic group still with retention of activity. Bigger R2 and R3 groups bind to the hydrophobic region outside the acetylcholine receptor site. In other words, you can see the small methyl group, it has its hydrophobic binding site, but once we introduce very huge groups, they will bind outside, outside that the area where the methyl group binds. So they are outside that area. We still have a hydrophobic area where the antagonistic groups bind, or this huge group binds to bring us antagonist activity. This is still going back to R1. The hydroxyl group at R1 presumably increases binding strength by participating in hydrogen bond interaction at the receptor. Remember, after you can see this ester, and we're removing that ester. So there must be an area which, of course, the ester is binding, usually with hydrogen bonds. So we are saying when we introduce a hydroxyl group, the hydroxyl group can interact with the area that the ester was interacting with through hydrogen bonds. And indeed, of course, that is our first one of the structures that actually obeys all those structural modifications that we have already discussed. Changes at the ester group, and we are saying that group can be totally removed. This subsequent may also be either oxygen, or it may be absent completely. So it can be removed completely. Remember, we have already got this one as an hydroxyl group, a hydroxymethyl group, and therefore we can be able to remove the ester. Although when it comes to, if you could have an ester linkage, you would have a very high anticholinergic activity, but you find that most of the drugs that we have normally do not have an ether, but they normally have an ester linkage. I mean, an ether linkage there, and with retention of activities. We can see benztropine mesylate, and it has an example. It's a good example whereby we have not completely removed the ether. We have actually replaced the ether group, the whole of this ether group, the whole of that ester group, the whole of the ester group with an ether linkage with, of course, retention of anticholinergic activity. Remember, we are going for anticholinergic now, not cholinergic activity. Then now we want to look at the amine. And we have already said in the acetylcholine, we have a quaternary ammonium ion. In these other drugs, which we are calling the anticholinergics, we bring in a tertiary amine because the anticholinergic is permanently charged. It can have issues of absorption or passage through the membrane. So you do have the tertiary amine, but we do know that in vivo it will be protonated to give us some, protonated to give us the ammonium ion. So compounds possessing the quaternary ammonium group exhibit nicotinic antagonist activity at high doses, so it will not be favorable. Quaternary ammonium compounds possess most potent anticholinergic activity. So the ones which are quaternary will possess nicotinic activity and also very, very high anticholinergic activity. But you find that is changed. So as we have said, to give us tertiary, the tertiary will have lower anticholinergic activity, but they will not have nicotinic activity. And therefore, that is a plus. Methyl, ethyl, propyl, or isopropyl groups are tolerated. But more often than not, the methyl groups are responsible for optimal activity. But we have seen that these R5 and R6 can also be part of heterocyclic rings, the nitrogen, and this can be part of heterocyclic rings. And whenever you have the rings, remember the groups, they can be ethyl groups, they can be ethyl groups, or perhaps propyl groups, but those groups within the rings are kind of shrunk because there is a constraint within the ring, and therefore you still maintain the distance that is necessary for optimal activity. Tertiary amines also possess an antagonist activity, presumably by binding the receptor in the protonated form. So we have said, although they are not as potent as the quaternary or in vivo, they will be protonated, and therefore they will interact with the receptor through they will interact with the receptor because they are still protonated. So please remember, we have said that the whole of that group can be part of a heterocyclic ring with retention of activity. And indeed, if you look at quite a number of the drugs, like this, very simple, you can see the nitrogen, the whole of the group there. So you can see when you look at now the two substituents, you can call that one as one of the substituents if you click there, You can see this is other 1, 2, 3 carbon atoms. So because of the ring brings constraint, and once it brings constraint, then you find that the compound is still able to interact with the receptor. But when it is straight chain, you find that the methyl is responsible for optimal activity. Then we look at changes at the R4, and the R4 is here at the middle, and we find optimum chain length is 2 to 4 carbon atoms. 2 carbon chain possesses the most antagonist activity. So you can lengthen that up to 4. But just like in acetylcholine, optimal activity is when R4 is 2 carbon atoms. And that, again, we can be able to see in almost all the compounds that we have, that length is 2 to 4 carbon atoms. That is 1. That is 2. In this one, the oxygen, remember, the oxygen replaced the ester. So you can see in this one is 1, 2, 3. We have said 2 to 4. So in that one, you can appreciate it's 3. I think that's the shortest. 1, 2, 3. Yeah. So in this one, in benzotropine, it is 3 carbon atoms, but we have said 2 to 4 with 2 carbon atoms being responsible for maximum activity. Again, if we go back, most of the other drugs, so we can see that is 2. You can see that is 2. This one we have counted as 3. We can see that is 2. 1, 2. So when you have that ring, it's a bit of a different structure of that ring, and you have that ring, and then you can only consider this carbon here. You can consider this nitrogen to be like this carbon there. You can consider this nitrogen because that ring there, you can consider this nitrogen to represent the carbon. And you can still see we have 1, 2. The difference between is 2 carbon atoms. And of course, it's a slightly different structure. As we have said, it is the phenothiazine nucleus, but it has still also been found to interact with these receptors. But this will not be one of the best drugs because it also has other interactions, and therefore it can be responsible for a lot of toxicity because it will also interact with other receptors. So that finishes the structural modification that has been done on acetylcholine to give us very good drugs that can interact with the muscarinic acetylcholine receptor antagonistically to give us antagonist activity, so that when we want to have a control of those 4 symptoms or those movements, or the reduction in movement or the problems in movement, then we will lower the acetylcholine. And of course, because it is the dopamine that has gone low, we will lower the levels of acetylcholine. There will still be a balance between the acetylcholine and the dopamine. The dopamine might still be a little bit low, but there will be a balance. So the movement will still be coordinated. And that is what we want. Tertiary amines are less potent receptor antagonists, but have greater selectivity for the muscarinic acetylcholine receptors versus the nicotinic acetylcholine receptors. And therefore, that selectivity is important because there is a reduction in toxicity. Also have antagonistic affinity for other receptors such as histamine, H1 and dopamine and D2 receptors. And that, of course, is responsible for toxicity. When you look at the antihistamines and so on, and even other dopamine receptors, you find that their agonists will also have the same structure. We can say tertiary amines have higher tertiary amines, when we compare them also to quaternary amines, have higher lipid solubility and therefore exhibit more favorable bioavailability. That is systemic and CNS, and that I had mentioned. The quaternary is a permanently charged ions, and of course the tertiary amines have slightly higher lipid solubility, better bioavailability, better penetration, better selectivity, and therefore lower toxicity. So the reason why we are mainly going for the tertiary amines and not the quaternary amines is the selectivity of, we have selectivity of the muscarinic receptor as compared to the nicotinic receptor, so that we do not block the nicotinic receptor because we would have a lot of toxicity. So that is, those are some of the reasons, and those are indeed the structural modifications, and we do have enough structures that demonstrate that you can change the acetylcholine to give you drugs that will go for that work as an antagonist at the muscarinic receptor. Then we are still on the anticholinergics. Anticholinergic medicines block cholinergic nerve impulses that help control the muscles of the arms, legs, and the body by inhibiting binding of acetylcholine with these receptors. Therefore, normal motor or muscle control, as we have already said, the effects of acetylcholine and dopamine need to be balanced. In Parkinson's, dopamine levels decrease, but acetylcholine levels remain the same, and cholinergic medicine decrease the levels of acetylcholine to achieve a closer balance with dopamine levels. That is what I've already mentioned. So that is now the anticholinergics. This is just an example of the anticholinergics. I believe we have heard of benzhexyl or the trihexylphenediol. Very important. It also is used in combination with chlorpromazine for management of psychosis. You can also add benzhexyl to chlorpromazine, because chlorpromazine, one of the side effects is the extrapyramidal effect. So again, you have tremors and so on. So you can also use benzhexyl, a very, very important drug, as in combination with chlorpromazine. So we are saying it's one of the examples we have given. It is an antimuscarinic drug that blocks the acetylcholine effect on muscarinic receptors. In Parkinson's, dopamine and acetylcholines are imbalanced that causes motor effects. Dopamine levels are reduced, and that I think is benzhexyl lowers the acetylcholine levels and maintains the balance. Trihexylphenediol is used for the symptomatic treatment of Parkinson's disease in mono and combination therapy with L-DOPA. So we are going to look at L-DOPA. So you can again use it in combination. Also used to control drooling of children with cerebral palsy. That's just another activity. In older patients with Parkinsonism, it can increase chances of dementia, since acetylcholine is involved in cognition too. So once you lower the activity of acetylcholine, again, you can enhance dementia. But so one has to be very in the drugs you give, one has to be very skilled. One has to observe exactly what is happening to the patient, because, as I have said, we are only controlling or managing the symptoms. So that's just an example. It is just doing what we had already explained. Or the only main important thing we have learned there is that you can use it in combination with L-DOPA. We used it in combination with L-DOPA. Remember, the L-DOPA will increase or will replace or increase the dopamine levels, and therefore help you to achieve the goal. Then we are still on cholinergic therapy, and the next one is the cholinesterase inhibitors. When talking, of course, these now are opposite of what we were doing. The others were antagonists. They were preventing acetylcholine from activity. These cholinesterase inhibitors are preventing the metabolism of acetylcholine, meaning that you can only use this one when the patient has dementia. So cholinesterase inhibitors are designed to increase levels of acetylcholine. Cholinesterase inhibitors do not stop the destruction of the dopaminergic nerve cells. Their ability to improve symptoms eventually declines as the brain cell damage progresses. And of course, we have said that with these ones, their only application is if the patient has developed dementia. When they develop dementia, it means the process is so progressive, it has not only affected the dopaminergic receptors or the dopaminergic neurons, it has also affected the cholinergic neurons, and with very low levels of the acetylcholine, you do require to decrease the metabolism of the acetylcholine. We have an example of rivastigmine. Again, when we look at these drugs, we will be able to understand how the structure of these drugs is a little bit different from that of acetylcholine. And when we say they are blocking cholinesterase enzyme from breaking down acetylcholine, it means they are binding the cholinesterase enzyme more strongly They are binding the cholinesterase enzyme more strongly than the acetylcholine, and therefore inhibiting it from breaking the acetylcholine as rapidly as when you have the acetylcholine versus the cholinesterase enzyme. So all that is happening is that these drugs, when they bind the cholinesterase enzyme, the bond is much stronger. The bond is much stronger. The hydrolysis of the complex between these drugs and acetylcholine is much slower. So there is a slowed rate of hydrolysis of acetylcholine, and there is accumulation of the acetylcholine, and as we have said, of importance in dementia. So we do have, it is the ribostigmine is an acetylcholinesterase, also a butyryl cholinesterase. This is what I think we call the pseudocholinesterase inhibitor used to treat dementia that sometimes occurs at later stages of Parkinson's disease. So this is usually at the latter stages. It increases late stages. It increases levels of acetylcholine by blocking its degradation from the enzymes acetyl or butyryl cholinesterases. This improves cognitive functions like memory and awareness. Some of the side effects are mostly nausea and vomiting, and at low doses, it is generally safe. It can sometimes dangerously slow the heartbeat, in which case atropine or acetylcholine blockers are used. And all we are saying, when we look at the mode of action, as I have said, if you look at this drug, let's look at the structure of this drug. Again, look at the structure of this drug. The other one had also drawn the structure of acetylcholine here. Remember, the acetylcholine has a CH3. And then it has a C double bond O. And then an oxygen. And then, of course, sorry. And then, of course, we are two the ethylene group. So if you look at this drug, the difference is actually here. If you look here, we have talked about an acetoxic group. But if you look here, we have a carbamate. And carbamate, because of stabilization by resonance, remember this has a lone pair of electrons. And that will move in, and this will move out. And once that happens, then the carbamate or this drug is more stabilized, because the carbonyl carbon does not really carry a positive charge, because the oxygen is already satisfied. It's not pulling away the electrons. But when you have the ester, this carbonyl group is withdrawing electrons at oxygen. This has a very strong delta positive, and therefore very easily attacked by nucleophiles. So all that we have changed when we look at the ribostigmine is the structure, whereby instead of the acetoxic group, the acetoxic group has been replaced by a carbamate. And the carbamates are more stable to hydrolysis because of stabilization by resonance. So what happens now is that when this drug binds the acetylcholinesterase enzyme, it binds the acetylcholinesterase enzyme, and the acetylcholinesterase enzyme will bind here to try and hydrolyze this drug. Of course, it will hydrolyze, but you find that when this carbamate or when the acetylcholinesterase enzyme is carbamylated, that carbamylated enzyme is more stable. That complex is more stable. It doesn't hydrolyze easily, and therefore it holds your enzyme, and therefore the enzyme is not free to go and hydrolyze other molecules of acetylcholine. So we are looking at this as the receptor here. So this is our receptor, and here is our drug. And as I have said, this is our carbamate. And of course, all these enzymes, as I've looked at them, they have a serine moiety. So this serine moiety, which has a lone pair of electrons, will attack that carbon there, and there will be a cleavage at that point. And therefore, you can see this is the enzyme. So here is our enzyme, or this is the surface or the receptor, which is our enzyme. So you can see at this point here, the enzyme has been carbamylated. So of course, this group goes out and the enzyme has been carbamylated. Don't bother about these other groups. Just draw your OH there attacking there, and of course hydrolysis coming at this position. And what is important here is that your enzyme is carbamylated. Once the enzyme is carbamylated, it is held a little bit more strongly, so there is slow hydrolysis. In other words, therefore, the enzyme has been held by this carbamate, and therefore there is slow hydrolysis to release the enzyme. Remember, the more of the enzyme you have, the higher the chance for this enzyme also going for the acetylcholine. And as long as the enzyme is held, it is not free to go for the acetylcholine, and hence the levels of the acetylcholine will go up because the acetylcholine is not being hydrolyzed, because the hydrolysis of the carbamylated cholinesterase enzyme is much, much slower, raising the concentration of acetylcholine. So that's the only difference. And all we are saying is that the rivastigmine is a carbamate, and it will carbamylate the enzyme, and the hydrolysis of the complex between the enzyme and the carbamate is much slower, allowing for the accumulation of acetylcholine. But we have said that that will be of importance at the end, whereby you do have dementia because of the degeneration also of the cholinergic neurons. So the ester inhibition, like for acetylcholine, is completely reversible. So that's completely reversible. The carbamate inhibition is semi-reversible. And this is all we have said. This is a serine moiety. This is now our enzyme. Remember, all our enzyme have a serine moiety, and the serine moiety has a hydroxyl group. That's the other portion of the enzyme. So that serine moiety, the hydroxyl group, coming in here, and as we have said, that moving out. So that is the enzyme carbamylating. That is the enzyme or the drug carbamylating the enzyme, and that carbamylation, as we are saying, is semi-reversible, meaning semi-reversible, it stays for a little longer held, and therefore giving us much, much better activity. Effective carbamylation is in the order shown below, and the question is why? Why would you think that the primary amines have a higher rate of are stronger carbamylators than that's the primary than the secondary or tertiary amines? Why would you think that the primary amines would be much better carbamylators than the secondary amines and even the tertiary amines? Can you give me your thoughts? Why would you think the primary amines are stronger carbamylators than the primary, than the secondary, than the tertiary? Can I get an informed idea? Not guessing. Why would you think so? This is chemistry that we have done. By the way, can we get an answer, please? Tuko tumelala. Are we there? Can't see anybody communicating. Kwani kumedaje? Anyway, when I see if you are quiet, then let me just okay, I can see Wambua Daniel. Just give it an informed, not guess, an informed answer. There can be two reasons. One is very obvious. One reason is very obvious. The other one you might not know very well, but there could be two reasons why the primary amines is more effective than the secondary amine and tertiary amine. Let me see what have you given me as the answer. Any answers yet? Any answers yet? I can't. No, it's not showing anything. It's not. We have not finalized with your typing. Primary. Yeah, only one person has answered. Primary aminophos, the steric hydrous, the carbomoyl oxygen, carbamoyl. Whereby we are saying, remember that this drug, the drug must have good accessibility to this carbon here for it to bring about any activity. So if you have a lot of groups there will be steric hydrons and of course a poor accessibility. But there is still another reason. Of course, the other reason, remember, whenever you have alkyl group, they are electron donors through sigma bonds. We have methyl groups, alkyl group are electron donors through through sigma bonds, and therefore they will increase the electron density of that carbon. And increasing the electron density of that carbon means it is not as reactive as when that is a hydrogen. Hydrogen has no influence on the electrons, but alkyl groups will donate electrons. In other words, they will also further stabilize. So when you have which one are we attacking? Let's see. This, you see, this requires to be highly electrophilic. And because it requires to be highly electrophilic, if you have groups that are also donating electrons into the system, those groups will reduce the electrophilicity of that carbon and therefore reduce its reactivity. So those two reasons can be the explanations to why the primary amine more active than secondary, more active than tertiary. One, issue of steric hydrons. Two, issue of methyl groups or alkyl groups being electron donors through sigma bonds and therefore decreasing the electrophilicity of the carbonyl carbon and therefore causing it not to be as highly reactive as, remember, even when we are looking at the beta block, we are calling them beta antibiotics, beta lactam antibiotics. Of course, we were talking about that carbonyl carbon, highly electrophilic. That's the same case here, that this carbon, for it to be attacked by the nucleophile of from the hydroxyl group of the enzyme, it requires to be reactive enough. Its reactivity is much higher when you have a primary amine compared to a secondary amine compared to a tertiary amine. But at least some we have tried. For those, I request you just keep trying. So that is that, and we have finished that. I think we are done with the cholinergic, the whole cholinergic, where it involves the anti-antagonists and the anticholinesterases. The anticholinesterases and the muscarinic antagonists, and we have given examples and we have shown how they work. So we move to the next category, and the next category is the dopaminergic therapy of Parkinsonism. And we start with the first category, which is a dopamine releasing agent. And you can see as from the name, releasing, they help to release dopamine. So dopamine, that dopamine which is being released must be somewhere stored. And normally the neurotransmitters, as I had said earlier, are stored in the vesicles. So this compound which we are giving must be taken up by the transport system that transports the dopamine. So there must be some slight structural similarities taken up. And then when it is taken up, it must be able to move into the dopamine vesicles and release. In other words, replace the dopamine within the vesicles and the dopamine is released. So that is what we're talking about. When you look at this drug, it has the amino group, but you can't see it has a cage-like structure. And this cage-like structure somehow hinders the metabolism of the amino group and also hinders the polarity of that group, and that drug is able to penetrate the lipid membranes and get the site of action. So amantadine displaces presynaptically stored dopamine into the synaptic cleft. This compound has a high pKa and therefore is extensively ionized at physiological pH. Mm-hmm. Just a minute. Okay. So we are saying this place, so it is highly protonated. But although it is protonated, as I have said, you see the cage-like. So it is protonated at physiological pH. However, it's cage-like hydrocarbon and adamantine. That is a cage-like hydrocarbon. That's the adamantine here. Structure provides lipophilicity and prevents oxidative metabolism. So that so that significant quantities of the drug can penetrate the CNS. So the cage-like structure is very important. Cage-like structure is kind of able to prevent the metabolism of the amino group. It also will give us enough lipid solubility, and the drug reaches the CNS in enough quantities. You don't need a lot, in enough quantity to bring its activity. The disadvantages associated with the use of amantadine include low efficacy. We are saying it is highly protonated. It will have challenges of penetrating. Not a lot of it will penetrate, so low efficacy and a dependence on the presence of presynaptic dopamine stores. You don't have any dopamine, then nothing will be released. So you must already have some dopamine stored, so that when you take your amantadine, then it gets into the storage vesicles and releases your your dopamine. my throat. Mode of action: it promotes dopamine release and prevents the uptake of dopamine in the CNS. Remember, before metabolism, you have to take up the dopamine for it to be metabolized. So as long as it is in the synaptic cleft, there cannot be metabolism. So it protects, it prevents. Remember, the metabolism is also an active, it uses active transport. So it will metabolism, prevent its uptake, and of course lower its metabolism. It promotes dopamine, adrenaline, serotonin, and blocks monoamine oxidase A and the N-methyl. Called what? N-methyl. It was it N. In those receptors. Yeah, N-methyl D-aspartate, I'd forgotten. So, so it promotes dopamine, noradrenaline, and serotonin, and blocks monoamine oxidase A and the N-methyl D-aspartate. It's a D which was bringing me a problem. N-methyl D-aspartate. So you find that it can also have some effect on other receptors, and once it blocks monoamine oxidase A and then these receptors, then of course also it will block the metabolism of dopamine. It has an amine group. We have said it has a very high pKa, but because of the cage-like structure, it helps in the cage-like structure help in preventing this drug being metabolized, and therefore it is able to get to the receptors intact. Of course, quite a lot of it will be metabolized, but it allows, at least, as we have said, quantifiable amounts to get the receptor for activity. Although mostly protonated in the blood, the unique cage-like structure provides a very high lipophilicity for good penetration into the brain. So remember, because of that cage, you have high lipid solubility. It's protonated at physiological pH, but at the same time, the cage-like structure still gives it good lipid solubility to allow it to penetrate. Also, as I have said, the cage-like structure also prevents metabolism such that it is excreted from the kidney in unchanged form. So that helps. The fact that the cage-like structure is preventing metabolism, because if there is metabolism, you can have oxidative end deamination, and the drug will not have activity. So the cage-like structure prevents metabolism. It also provides enough lipid solubility, and that drug can penetrate the BBB and get into the brain and replace. It is just release or replace the dopamine within the vesicles to bring us activity. As we have said, that is its main mode of action. The others are just added to that. The synthesis, simple synthesis, you have that is the adamantane, as we've already said, and you can either do bromination, or you can have nitration, and when you brominate, you get the bromine there, or when you do nitration, you get your nitrate there, And then you can use the nitrile, methyl nitrile in sulfuric acid, and it will give you that derivative, finally give you the compound. Well, you can do for me, get the names of all these compounds. So we are reacting adamantine. So the first one we've already said, adamantine with bromine or nitric acid to give the bromide or nitroesters. So you can see the bromide or nitroesters at position 1. The reaction of either of the compound with acetonitrile, so already you have that name, affords the acetamide. So that is the acetamide, and you can see it is the amide, acetamide, which is hydrolyzed to give the one adamantyl amine, all adamantine. So I think it's just putting the names, they're already there. So that is a very simple, this I said I can give us because it's a very simple way of synthesis of the adamantine. Very, very simple way of synthesis. And that is all I have on the adamantine. Sorry, amantadine. On the amantadine, it comes from the adamantine. So amantadine, as we have said, is a good drug, but it relies on already existing dopamine storage. You must have dopamine within the vesicles. If you do not have, then you have a challenge. We are also saying it has its own challenges of low efficacy, so it has a very, very low efficacy, and of course relying on those stored quantities. If you do not have them, then the drug will not have activity. So the next one is, so that was dopamine release, and you can understand it's releasing dopamine from the receptors. Then you have the dopamine replacement, and in dopamine, if you are replacing, then you must bring an alternative, something that you are replacing the dopamine, and therefore you must bring something that can generate the dopamine. So actually, when we look at the dopamine, as we already said, it has some it has limitations in that it cannot be able to penetrate the BBB, and of course also if you have that dopamine in the periphery, it can cause a lot of toxicity. So exogenous replacement of dopamine in Parkinsonism or Parkinson's patient is unsuccessful because dopamine cannot access the CNS from the periphery. It will not. If you give it as dopamine, it will not cross. It has a lot of limitations. It will cause a lot of toxicity. It has a lot of limitations, and one of the limitations is structural hydrophilicity. It has structural hydrophilicity, and therefore that will not allow it to pass the BBB. There is ionization. It's a basic compound with a pKa of the amino group at 10.6. Therefore, it is primarily protonated at physiological pH. Again, so the hydrophilicity as it is, and then the protonation or ionization at physiological pH, again increasing its polarity. And then it has metabolic liability. There will be peripheral deamination, and conjugation also limits systemic utility. So you cannot be able to replace dopamine with dopamine and you expect that dopamine to get into the brain. No, you can't. You must find a way out, and the way out of replacing dopamine is replacing it with L-DOPA. And L-DOPA is a dopamine precursor. So synthesis of L-DOPA from tyrosine, that is again a very simple way of synthesis. That is our tyrosine, and then you use hydrogen peroxide, ferrous sulfate, and some heat. And once you do that, then you form the catechol. You can see that is a hydroxyphenyl derivative. Then you form the catechol, and so this is where you know dihydroxyphenyl alanine. Dihydroxyphenyl alanine. So all we are doing to tyrosine is actually adding an extra hydroxyl group. Of course, a hydroxyl group at ortho position to already the existing hydroxyl group to give us our L-DOPA. And the L-DOPA is now what we will use as a prodrug for the release of dopamine. So we can look dopamine replacement. Exogenous also administration of dopamine will produce a variety of adverse effects as a result of dopamine interacting with various monoamine, noradrenaline, 5-HT, also dopamine receptors in both the CNS and the peripheral nervous system. So we are saying that that's also an addition of the complexity here. There is structural hydrophilicity, there is ionization, there is metabolic liability, and there is also increased toxicity or the side effect when you give it peripherally, the dopamine will bind other receptors, including also the dopamine receptors peripherally, and it will give you a lot of toxicity. So effective delivery of dopamine to the CNS is achieved by the use of exogenous biosynthetic precursor. So we do not use, we cannot give dopamine. It's important for us to understand the 4 reasons why we cannot give dopamine, but we are able to give the dopamine precursor L-dihydroxyphenylalanine or L-DOPA, which one accesses the CNS site via an amino acid transporter. So this has its own transporter, an amino acid transporter, as opposed to dopamine, and therefore it will concentrate in the CNS, is readily decarboxylated in dopaminergic neurons to dopamine by dopa decarboxylase. So that those 2 reasons allow us to use L-DOPA. But of course, we do have the disadvantage that, as I had said earlier, that the L-DOPA will also undergo decarboxylation in the periphery to give us dopamine in the periphery. Once it undergoes decarboxylation in the periphery to give us dopamine, then you will have the issues that we did not want to have. And that, of course, we are able to sort it out very easily. And we're going to get to that. Significant concentration of dopamine are formed in the periphery related to periphery because of the dopa all due to metabolism by dopa decarboxylase activity, giving rise to periphery dopamine stimulation or primarily cardiovascular effects. So this can be a big problem of the dopa decarboxylase or the dopa dopa undergoing decarboxylation, and once it undergoes decarboxylation, it will release dopamine, and some of the things we are saying we do not want to encounter, we will encounter them, and no wonder the need for a periphery dopa decarboxylase inhibitor. So that is why there is development of a dopa decarboxylase inhibitor, which acts in the periphery to preserve the L-DOPA in high concentrations. The L-DOPA penetrates the BBB in high concentrations. It gets the dopa decarboxylase does not cross the BBB, so the L-DOPA gets into BBB. It now undergoes decarboxylation within the brain to give you high concentrations of dopamine, and those high concentrations of dopamine now will help us, of course, to relieve the symptoms of Parkinsonism. So when we look at the metabolism of dopa, it's easier to look at it here. So we have the L-DOPA, that's what we are giving, L-DOPA. So it can undergo metabolism by catechol methyl transferase. If that happens, you will get the 3-O-methyl dopa. Of course, the numbering must start from the lower one, so it will be 3-O-methyl dopa. Or it can be metabolized by the dopa decarboxylase. This is the aromatic amino dopa decarboxylase, and if that does happen, you will get your dopamine, and this is in the periphery. Or L-DOPA can cross through the brain, the blood-brain barrier, get into the brain, and again in the brain, it can be undergo decarboxylation. If it does do that, it will get us now to the dopamine, but this dopamine is the brain. So before it undergoes the metabolism in the brain, it's already, you have high levels. But I've signed in again. You can hear me? Can you hear me? Please tell me whether you can hear me. Yes, okay. I don't know what happened. I was just removed from the meeting. So all I'm saying is that, of course, when the dopamine gets into the brain, it will still undergo other metabolic processes. And that is why we also have drugs. We did mention when we were looking at the classification, we do have drugs that will inhibit the monoamine oxidase. We do have drugs that will inhibit the catechol methyl transferase, so that will increase the dopamine levels for a slightly higher level. So we increase the dopamine levels. But as long as we have given the dopa, at least we are at a good position because we have already increased the dopamine level. So that's what we are saying. And as I was saying, it's a reverse. If you start with the monoamine oxidase B, the next one will be the COMT. If you start with COMT, the next enzyme will be MAOT. So you can look at them. They can be they can be reversed. You start with one or the other. So if you look at the metabolism, so it is just, this is the same as here. So we are saying the L-dopa can be metabolized by the catechol methyltransferase to give us a 3-O-methyl dopa. And that is, you can see catechol methyltransferase transfers its methyl group on to one of the hydroxyl groups. Or you can have the aromatic dopa decarboxylase giving us the dopamine, and then the dopamine now can be acted on by the monoamine oxidase to give us dopac. Or, and then if it has been acted on by the monoamine oxidase, the next enzyme which will act on it will be the catechol methyltransferase, which will transfer the methyl group again to the position 3 hydroxyl group. So all it can, of course, as we had said, it can start the catechol methyltransferase, where you transfer the methyl group first, and then the 3-methoxytyramine now undergoes the oxidation through monoamine oxidase B. So that is the route of metabolism of the dopamine, and that is why we also have those other drugs, as we have said, that can be used to block the metabolism of dopamine. So the dopamine replacement, addition of a dopa decarboxylase inhibitor, carbidopa, improves the CNS bioavailability of L-dopa. That is exactly what we have said. So you have your L-dopa there, L-dihydroxyphenyl alanine, and once you have that, then you give an L-aromatic amino acid decarboxylase inhibitor. Once, because that is the enzyme. This is the enzyme that is metabolizing to dopamine. You give the dopa decarboxylase inhibitor, and one of them is carbidopa. So you can see, again, you can, as we have always said, you can see there is some structural resemblance and some structural difference. You can see that is that catechol is still there, and then you have the CH2, and then you have this group there, which has a carboxylic group, and it is substituted with a methyl group. So this, it has an extra one, so it has that carbon there, it is that carbon there, and then this carbon, which carries the amino group and the carboxylic group, has also a substitution. So it has a methyl. The hydrogen of this carbon has been replaced with a methyl group, and at the same time, our amino group has been replaced with a hydrazine. We look at this group there. So there is structural resemblance, a lot of structural resemblance with the dopamine. So if you look at the L-dopa and the carbidopa, there is a lot of structural resemblance, because you remember both of them will be acting as substrate for the same enzyme. And the enzyme means if it is an inhibitor of this enzyme, it means it blocks, it binds that enzyme more strongly than the L-dopa. That's all it means. It binds the enzyme more strongly than L-dopa. And as it binds the enzyme more strongly than the L-dopa, again, as we said earlier, the enzyme is not available to metabolize the L-dopa. So there must be structural resemblance, because these two are indeed substrates of the same enzyme, but there will also be some structural difference, so that after the enzyme recognizes the carbidopa as a substrate, there is some structural difference that allows the enzyme to bind the carbidopa more strongly. And that is why you can see, in place of the hydrogen, you do have this, you do have a methyl group there, and in place of the NH2, you have a hydrazine. That's a hydrazine there, and NH2, which is again protonated at physiological pH, just like the L-dopa, to allow it to bind the receptors, as we have talked about. So therefore, there is structural resemblance, but also structural difference between the L-dopa and the carbidopa that allows the carbidopa to bind the enzyme more strongly, and therefore inhibit it from metabolizing the L-dopa to dopamine, and hence the L-dopa is able to be in high concentrations, penetrate the BBB, get into the brain where it brings about its activity. It is absorbed well from the small bowel, peak plasma levels, and may be delayed in the presence of food. The rate of absorption is dependent on this. This again, pharmacokinetics. You should be able to do a lot of it when you look at pharmacology. The rate of gastric emptying, period of gastric squeeze, the length of time the drug is exposed to the degradative enzymes of gastric mucosa and intestinal flora. So that is just showing the effects, how the absorption can be influenced by other factors. The drug is extensively metabolized in the periphery and by the liver. I believe that is the L-dopa, very low amounts, less than 1% of the unchanged drug penetrates the CNS. Plasma half-life ranges from that to that. It is excreted primarily in the urine. The major urinary metabolites of levodopa appear to be dihydroxy. I think I've gone back. Dihydroxyphenyl acetic acid, dopac, and homomanilic acid. That we had already seen. I'm sorry, that was this is metabolism and excretion of the L-dopa, and we have said it is metabolized very rapidly, and therefore it will require to have a way out so that we preserve it. So in the treatment, this is what we are saying we have done, and we have already discussed that. That's the levodopa. So the levodopa will be metabolized by the dopa decarboxylase very rapidly, and very little of it will get into the brain. Very little of it will get into the brain, and then of course, when it gets into the brain, as the dopamine gets into the brain, it is changed into the dopamine. Of course, a bit of it will get in, change into the dopamine, and then of course the dopamine, as we have said, the dopamine will be metabolized. This is the same thing we have said, metabolized by COMT and so on, and that again requires us, and that's why it requires, and this position is where we are putting the carbidopa or the dopa decarboxylase inhibitor, and in doing so, it helps us in getting this drug here, not as dopamine, but a high concentration of that drug there as L-dopa, and then metabolized to dopamine within the brain rather than peripherally. Of course, here we are just showing that some of the dopamine, of course, as we had said, will enter the vesicles, and this is how we are able to use the adamantine, because it is amantadine, sorry, because it is able to release this dopamine from the vesicles. That is just what we have been saying. So when we look at carbidopa, for which we have looked at the structure, we have looked at the structure. It has the NH2, which of course we have said is a hydrazine. Then we have the methyl, which gives us a slightly different structure from what we have with the L-dopa. We are saying the carbidopa is a pyridoxal dopa decarboxylase cofactor. In other words, by saying it's pyridoxal, it uses pyridoxine as a cofactor. It is a dopamine decarboxylase inhibitor. Its purpose is to increase the efficacy of L-dopa by preventing its peripheral metabolic degradation. Inhibition of L-dopa decarboxylase allows more L-dopa to penetrate the brain. Dopamine decarboxylase exists both inside and outside the brain. Carbidopa only blocks metabolism outside the brain because it cannot penetrate the brain. You have the dopa decarboxylase in the periphery and in the brain. We require the one in the brain so that when the L-dopa hits the brain, it cannot undergo decarboxylation to give us dopamine in the brain. We do not require the decarboxylase within the periphery because it will give us dopamine with a lot of challenges. So we block that one, and then the L-dopa gets into the brain, releases the L-dopamine, and we are good to go. So we can be able to say that this structure of carbidopa is such that it is structurally modified, as we have already said, to bind the enzyme more strongly and therefore release and therefore allow for the L-dopa to concentrate in the brain. So that's our carbidopa, and we are only saying it. You can see this is our pyridoxine. We are only saying that is our dopa, and this is the pyridoxine, and that's why we have said the dopa decarboxylase has a pyridoxine, or has pyridoxine as its cofactor, and therefore when it comes to carbidopa, you can see the carbidopa is also binding. It's binding on our cofactor, the pyridoxine. So the dopa decarboxylase, we have our pyridoxine cofactor, and then that is bound by our drug, and in being bound by our drug, then our enzyme is held tightly and does not bring us the activity that we require. And you can see that the arrow for forming this complex where our enzyme has been bound is much longer and bolder than the hydrolysis of this complex, meaning that the enzyme is held a little bit longer, and in that way it is not available, as we have said, for the metabolism of the L-DOPA. So that finishes the ones for replacement, mainly being L-DOPA, and the necessity for us to combine L-DOPA with carbidopa. I hope I've explained it well. Dopamine receptor agonists, and these are drugs that you just bind the receptor just like dopamine, and therefore reinforce or enhance the activity of that dopamine. They reinforce the dopamine neurotransmission in the substance nigra by postsynaptic receptor activation. They reduce dopamine biosynthesis and turnover by activating presynaptic autoreceptors. So they will also they reduce dopamine and biosynthesis and turnover. That means it's being converted or it's being hydrolyzed. They will reduce that, and therefore the dopamine will be there for a slightly longer time. They will bind the receptors and therefore give us the same effect as if it were dopamine itself. And then we have two types, as we already said. We have the bigger molecules, the more complex molecules, which are egoline or ergot derivatives, and under this we have bromocriptine. All egoline derivatives are structurally derived from the alkaloid products produced by the grain fungus Claviceps papyri. Natural and semi-synthetic compounds having high affinity, both agonistic and antagonistic, for monoamine, noradrenaline, dopamine receptors. We have an example of bromocriptine. So we are saying they are not highly selective for dopamine. They can also bind noradrenaline receptors, and no wonder they will be responsible for quite a number of side effects. So bromocriptine, mesylate, and the more potent pagolide, we have these two, bromocriptine and pagolide mesylate, are dopamine receptor agonists used as adjunctive treatment to levodopa in controlling the symptoms of Parkinsonism. These are derivatives, ergot derivatives, naturally occurring compound. Affinity of egoline derivatives for dopamine receptors is presumably related to the presence of an aryl ethylamine structural feature in these drugs. We are going to show that in a minute. So when we look, this is the egoline. These are the egoline derivatives. That is the structure there. So they will have the egoline derivatives. We have this alkaloid. This is the one we are calling the alkaloid. So they will have that. And all of them, when you look at them, you will see this structure here. That one there. If you look at this, you have that. So they will have that. And if you look at that, for sure, you remember not only that and that. If you look at dopamine, dopamine has a phenyl ring, which we said was separated with 2 carbon atoms from the terminal. And it's also tertiary. So even this one, you can see this is also tertiary amine. So because of that structure, the aryl ethyl amino structure, then these drugs can go for the dopamine receptors, bind the dopamine receptors, and bring about some activity. So these other ones are just other groups which you can have substituted. When you look at also pagolide, you can also see that what we have looked at, the same here. Then you go like that, and you go like that. And again, we are able to see the tertiary amine there. We are able to see the 2 carbon atoms, and we are able to see the phenyl group. So that is what we are saying. That group, the aryl ethyl amine structure, which is found in these drugs or egoline derivatives, or in these ergot derivatives or egoline derivatives, is thought to be the reason why they are able to bind the dopamine receptors. But as we have said, they will not be selective for dopamine receptors. They can also bind other receptors to bring about toxicity. So you can use them, but of course we have better drugs which we are going to look at. So we have bromocriptine. As we have already said, it is an egoline derivative. It's a dopamine organ agonist that is used in the treatment of Parkinson's disease. Again, of course, in the control of the symptoms have you already said. It is a dopamine agonist. It's a compound that activates dopamine receptors in the absence of dopamine, used with levodopa, carbidopa to prolong the effectiveness. Of course, we've already mentioned where there it helps, that will increase the dopamine levels. Whatever little you have, it will be preserved. It will be, whatever. These ones will bring in new dopamine amounts, and again also the drug you are giving as bromocriptine or pagoline again will be also exciting the receptors. So when you do all that, you are bringing in a replacement. You are also having agonists which are binding. If you have any, remember we were talking about that there is a degeneration of the dopaminergic neurons. So if you have any receptors that are remaining, then they can be activated by these dopamine receptors, as we have seen an example, bromocriptine and of course of pagoline. These are the naturally occurring, of course, having quite complex structures. Then we have the non-egoline derivatives, which of course do not have that alkaloid structure, and these are structurally simpler dopamine receptor agonists compared to the egoline derivatives or the ergots. The spectrum of receptor activity is much more focused. When we say much more focused, all we mean is that it's more selective. They will go more for the dopamine 1 receptors than other receptors, and ergot, leading to lower toxicity, lower interaction with other receptors, including the serotonin and noradrenaline receptors. Because when you look at the drugs, or if you look at serotonin, if you look at the noradrenaline, all of them do have a tertiary amine. And because of the structural similarity, they have a phenyl ring. Because of those structural similarities, then you find you must be very careful the drug that you bring in. It has to have high selectivity, because if it doesn't have high selectivity, because all of them will have a tertiary amine protonated in the blood, if it doesn't have high selectivity for the specific receptor, then for sure it will interact with other receptors, and interacting with other receptors, then it will be responsible for a lot of toxicity. So when this is one of the drugs, opinirole and pramipexole, and those are the two drugs. And you can see again the hydrochloride salts, the drugs majorly hydrophobic, and of course the salt derivatization is for the purpose of solubility in the GIT, so that you can get enough that can be able to be absorbed. Look at this, you have that as one of the nitrogens that forms the salt, and that one. Here you have that one as the one which forms the salt. So if you look at pramipexole, it's a tetrahydrobenzothiazole. So this is the one we're calling the tetrahydro. This one, tetrahydrobenzo, because you can see it's a derivative of benzene where there is saturation of 2 double bonds. So you have added four hydrogens, and no wonder tetrahydrobenzo, because it is a derivative of benzene, but with saturation of the 2 double bonds. That bond there has been saturated, that double bond there has been saturated, and no wonder the tetrahydro. Then, of course, diazole, which all of us can see that is a thiazole ring. Indeed, it is an aminothiazole. That's a ring we have discussed a lot when we were discussing the several sporins. So that's why we are calling it a tetrahydrobenzothiazole derivative, formulated as a dihydrochloride salt, side chain NH, and the heteroatom nitrogen are the ones that are protonated when we are formulating the salt, again for purposes of increasing the solubility. Pharmacologically, it has an active single stereoisomer, which is the S laboratory isomer. Again, if you look at it, we can look for the chiral center, and you can see that is a chiral center there. I think that's the only chiral center it has. And because of that chiral center, you can see that group. That is a group. That group there, that is the amine group, or the amino side chain, because of course that group of the amino group there, that is 1, 2, 3, the propyl amino group, propyl amine group there. When you look at it, it is carrying the beta orientation, whereas the hydrogen is carrying the alpha orientation. And I believe the beta orientation of the propyl amino group and the alpha orientation of the hydrogen is the one which is responsible for the liberatory, the S liberatory isomer. S, you know what it stands for. Liberatory, you know what we are talking about, because we've done all that, and we are saying that is the active isomer. So again, the stereochemistry again coming in this drug and showing that one isomer is the one which is active. It possesses a low oxidation potential. If something possesses a low oxidation potential, it means it can be used as a reducing agent because it is not readily oxidized. So if it has low oxidation potential, it can be used as a reducing agent when itself gets oxidized. And that's one of its mode of action. It possesses a low oxidation potential, which may function to scavenge. That is high tendency to be oxidized and act as a reducing agent for neuroprotection. That is when you look for dopamine-derived free radicals and electrophiles. In the body, the dopamine can be oxidized to free radicals and electrophiles, which can cause a lot of damage. And therefore, this drug can act as a reducing agent to reduce those oxidation, to reduce the oxidized dopamine, and therefore protect again the cells, protect the neurons from the activity, the dangerous, the free radicals and the electrophiles are highly poisonous metabolites, and therefore protect the neurons from these highly toxic metabolites, and of course preserve them because they are already undergoing degeneration. They do not need any other poisons or any other toxic compounds or metabolites. Already they have their own issues. So that is pramipexole, whereby we are saying it has a low oxidation state, and therefore can also have that activity. So it can have that activity on top of it being a dopamine agonist. It can also preserve the neurons from toxicity by the dopamine oxidized states. So we are looking at the dopamine, and now we are saying that in the body, the dopamine can undergo oxidation to these compounds. So you can see these are oxidized compounds, superoxide radicals and electrophiles. So these are strong electrophiles. They are, of course, also this is the superoxide radical, which can be very toxic. And you can see also this as very strong electrophiles. And we are saying the pramipexole can be able, because of its low oxidation state or all oxidation potential, it can be able to reduce these compounds and retain them in the safe state. And therefore that, so it can be said to have those two ways of activity. Then you have the lopinol and indolinone. Again, if you look at this is the indo, but the indo under normal circumstances has a double bond. Indo normally has a double bond, and therefore once you remove, you have put this double bond here, so you cannot, of course, you have put the ketone there, and therefore that's why we're calling it an indolinone, and the none is because of this. If you remember when you were drawing the indo, it usually has a double bond at that position. But you can see that double bond has been removed. It usually has a double bond there. That has been removed, and therefore the nitrogen has a hydrogen, and therefore that's why we are not calling it an indo, but we are calling it an indoline. It would be an indoline because of that saturation or reduction of the indo, and then at the same time it has also a carbonyl group. The carbon, one of the carbons has been oxidized to give us the own. So that is again where the name is coming from. Again, when we look at it, you can see it has that. Again, it has some maintenance. It has a structural similarity. Again, there, if you look at it, structural similarity for sure with dopamine, and therefore it can be able to go for the dopamine receptors and act as a dopamine agonist. It has a high affinity for the dopamine receptors, the D2, the D3, and D4 subtypes, formulated for oral administration also as a hydrochloride. So again, when we look at these compounds, we are realizing for them to bind the receptor, of course, they must have structural resemblance. They are able to bind the receptor more strongly, of course, quite strongly. They are agonists. So when they bind the receptor, they are also able to trigger the biological activity. And that's the difference between an antagonist and an agonist. An agonist triggers a pharmacological or a biological activity. The antagonist binds very well into the receptor, but because of its structure, it is not able to trigger a biological activity. So it just acts as what we call the dog in the manger, blocks the receptor from the agonist, and yet it cannot bring about any pharmacological activity. So the antagonist never triggers, never excites the receptor. It blocks the receptor from access by other drugs. Do we have any question up to there? Any question, class? Any question up to there? None. I can see we are okay. You're supposed to go up to what time? We started late. 9:30 to 11:30. So I just have a few more minutes. We started quite late. Then we have another drug, which is also a dopamine agonist, and it is called apomorphine. Of course, the name morphine here does not bring any structural resemblance with morphine. It's just a name. So apomorphine, it has no relationship with morphine, but it is just a drug that is its name, and it's a drug that was also found to be a dopamine agonist. And its structure and stereochemistry, apomorphine is a beta-phenyl ethyl amine. Again, the same thing that we have discussed. Again, look at that. So it's a phenyl ethyl amine. So again, the same as we had already discussed. So it's a beta-phenyl ethyl amine, sharing structural similarities, the neurotransmitter dopamine. Dopamine, it has a catechol, so it's why it has a catechol moiety, it has an ethyl amine group. And therefore, because of that, again, structural similarity, then it can also be able, you can see the dopamine structure, it can be able to bind the receptor and bring about some biological activity. Apomorphine is a chiral molecule. Again, when we look at it, we should be able to appreciate where is its chirality. If you look at this carbon layer, which again has a chiral center there, and because of that chiral center, just as we have mentioned before, then you can have, we know this, you can have a stereochemistry, and you find that the R form is a dopamine agonist, whereas the S form of the molecule may possess antidopaminergic activity. Again, there is no strictness like in some of the other drugs that we have mentioned, because you can see for pramipixel, we mentioned that it is the S isomer, which had activity. But now for this one, you find that there can be differences. So there is no, that one was S, and you can see this one is the R. So there is no strictness into as to whether it's a dextro isomer or which isomer does bring about activity. So R form is a dopamine agonist, whereas the S form of the molecule may possess antidopaminergic activity. So therefore, you'd require to have R, to also the levo isomer, R levoapomorphine, because if you have the S, then as you can see, you will have antidopaminergic activity, and that will worsen, of course, your Parkinsonism, and you will not want that. Physical chemical properties of apomorphine. It is water soluble with an intermediate lipophilicity, and is generally available again as the hydrochloride salt. Again, normally we derivatize them into salts to further improve the water solubility. Of course, we are saying it has quite some appreciable water solubility. It is a catechol derivative, and you can see it has also that amine there. So that, I believe, is what has contributed to its water solubility. The hydrophilic character of apomorphine allows it to be solubilized and therefore formulated also as an aqueous solution. Because we have said it has good water solubility, it can be formulated as an aqueous solution. It readily mixes in tissue fluids and can be absorbed into the systemic circulation and subsequently crosses a lipophilic blood-brain barrier. It has enough. It has both appreciable lipid solubility, appreciable water solubility for it to be able to be soluble. Apomorphine therapy. Some Parkinson's disease patients develop what we call on-off phenomenon with a prolonged L-DOPA use of greater than 5 years. When we talk about on-off phenomenon, they are on the drugs, but they are still having the symptoms of Parkinsonism. So sometimes they are okay, other times, although they are on L-DOPA, because of using it for a long time, they develop the off phenomenon. It is like they are not on the drug. So that's what we call on-off phenomenon with prolonged use of L-DOPA. Apomorphine, it's a mixed D1, D2 dopamine agonist, predominantly finds its use as a rescue medicine to treat the off period in L-DOPA therapy. So that is so it's an important drug because, as we have said, we have already said, it's a terrible disease because we are giving drugs and they can only manage the symptoms, no cure. Indeed, the problem is worsening because the dopaminergic neurons are degenerating with time. So it can be quite a debilitating disease. The D1 potency by apomorphine is exhibited by the catechol moiety, where the baroaromatic part of the molecule contributes the affinity to do D2. So we are saying it can bind both the D1 and D2 receptors. Unlike oral L-DOPA therapy, apomorphine is administered subcutaneously. And you can be able to administer it subcutaneously, that is parenterally, because we have said it has good water solubility in the abdomen region in an intermittent injection or by continuous infusion using an infusion pump. So you can give it, inject, and inject, and then you can inject severally during the course of the day, or you can give it continuously with an infusion pump. So that is an important point to note. And you can't give it, it is not given orally, you give it subcutaneously. The avoidance of dyskinesia that we call abnormality or impairment of voluntary movement. Remember where we said somebody has poverty of movement is a major advantage of apomorphine treatment over L-dopamine therapy. So it is able to manage the abnormality or impairment of the voluntary movement. However, apomorphine administration has several disadvantages such as nausea and vomiting. That requires antiemetics, which are often co-dosed, such as domperidone. So we are only saying it has that side effect, but you can give it together with the antiemetics for you to avoid those side effects. So administered subcutaneously, quite good in control of impairment of voluntary movement. Again, we have said a very good drug which you can give in case the patient has started developing the off period, even when they are on L-DOPA. So those are some of the good effects, but unfortunately, it will have its bad effects, but which fortunately, we can be able to control. Subcutaneous apomorphine therapy may give rise to problems with patients, compliance associated with, of course, whenever you give a drug parenterally, you do have those issues. Of course, parenteral administration is more expensive. It is, of course, it can cause more side effects. I mean, not side effects, but more toxicity in that you can get sepsis and so on. And of course, if you have patients, you can have a problem in patient compliance. In case you have patients who fear the needle or who have needle phobia, of course, you can have local pain due to irritation and inflammation followed by a formation of subcutaneous. Giving drugs parenterally is not the best. And again, you can see now, you're saying this patient, this disease is a chronic disease. So this patient, if they have to use they must do the injections. And remember, subcutaneous in the stomach. And you know how sensitive the stomach is. So that, of course, can cause a lot of pain and can have problem with patient compliance. Subcutaneous, again, the other themselves. Subcutaneous, even for insulin, we do it subcutaneously. But again, that's where we are saying patient compliance. When they remember the pain of injection, when again we are saying on continued injection, you can have the nodules, you can have swellings and the stomach hardening and so on, then that can be an issue of administration or patient compliance of this drug. But we have said it has its advantages. So it will be the patient way whether they want to cope with the off periods when they will have problems of movements, they can fall, they have rigidity, or whether they will be able to withstand the pain of administration and the issues of administration and get over and not have the off period of Parkinsonism. So that will depend on the patient, or the patient will perhaps opt to have, of course, the expensive way of going to have it injected, and that is a decision the patient must make. And of course, when we give drugs, we want to give drugs that have got very high compliance and are not inconveniencing the patient, but at times you do not have a choice. Challenges with the apomorphine therapy. And we find that we do have a few challenges with the apomorphine therapy in that it is very unstable, it has very high instability, it undergoes very rapid metabolism, and that can be quite a challenge. So one of the challenges of apomorphine therapy include inherent instability poses a complication in clinical practice. When you have a drug that is highly unstable, it will bring about a lot of complications because you must store it very well. And by the time you remove it from the vial and you are transferring it to inject it, that is enough time for that drug to go undergo degradation because it has very high instability. By the time you inject it again, it will be exposed to oxygen. By the time you're injecting it, getting into the body, you also do have some fluids. And therefore, when you have a drug which has high instability, then it is a challenge for administration. And one of the challenges is oxidation of apomorphine is one of the pharmaceutical challenges when it is formulated as an aqueous solution. So that, and we have said it must be formulated as an aqueous solution, yet it has very, very high instability. Also, apomorphine spontaneously undergoes oxidative decomposition in aqueous solution to yield a bluish green color in the presence of light and air. Go to Auntie. All right. So not only does it have the challenge of oxidation, also when it's in contact with light and air, again it will undergo again spontaneously undergoes spontaneously, which will undergo change, or it will undergo spontaneous decomposition. This is not really, it's oxidative decomposition, but it's a little bit different from the oxidation. Oxidation is just oxidation. This is what we are calling spontaneous oxidative decomposition. So again, it will change in structure and not have any activity. The catechol group of the apomorphine molecule again is highly susceptible also to oxidation, leading to the formation of a quinone. So those are challenges of the instability of apomorphine, especially when you give it at an aqueous solution, and therefore can hinder, especially when you have the patient being the one to inject themselves. Then you might find that they're injecting themselves compounds that have no activity. The decomposition of apomorphine is dependent on its concentration as well as the pH and temperature of the solution. The chemical half-life of apomorphine is very short at physiological condition. The additions of antioxidants, chelating agents, or alteration of the formulation pH are some of the approaches to prevent the auto-oxidation of the molecule. So again, there are still some ways to solve the problem by adding antioxidants, chelating agents, altering the pH, because we have seen the pH also and temperature are catalysts of the degradation. They are catalysts of the degradation. Then you find that you can formulate it and put antioxidants, slow down the oxidation or the decomposition or the degradation, but it is still a challenge. I think we can end there. What's the time? Yeah, 11:34. become also exhausted. So we have quite a little to go. That's why I'm not worried. So we can end there on the challenges of apomorphine. And I believe we will finish next time. Not only will we finish, because we have just a few slides to go, not many. We will finish with the anti-Parkinsonian drugs. And I think we will look at, after this, we will look at, I think after this, we can look at the general anesthetics. As I said, this unit has very many to small subtopics. So we are done with the narcotic analgesics. I am promising by next week we should finish with the anti-Parkinsonian drugs and start with the general anesthetics. So we can do some reading on the general anesthetics, try to classify these drugs. For the general anesthetics, you will find that this is one class of drugs, and like the other classes of drugs that we have looked at have no structural semblance. You have drugs with very different structures acting, apart from, of course, perhaps the barbiturates. You have drugs with very different structures acting as general anesthetics, and really, apart from within the same class, we do not have a lot of SAR in these drugs. This is because we say these drugs just act. As long as the drug has good hydrophobicity and can be able to sit on the neuron and block that neuron, then that drug does have activity. But you can also classify the various general anesthetics. Do classify them usually according to, we have the intravenous, we have the hydrocarbons. In fact, we classify them according to their structure. In other words, we have, or according to their route of administration. Actually, we are classifying them according to the route of administration, where you can have the intravenous ones, you can have the ones the ones that are given orally, the intravenous, and the ones that are also the ones that are given not orally, intravenous, and the ones that are given through inhalation. So you classify them. You can classify them to those ones which are intravenous and the ones that are given according to the inhalation. And then, of course, when you come to the ones you give through inhalation, you can further classify them now according to their structures. So the ones given by the inhalation, again, you can classify them according to the structure. So that will be the next class. Again, it's a very simple class. That one, I think we might be able to be through it in one lesson. So then after that, we will look at the hallucinogens, and we'll be nearing the end, I hope. So please look at those drugs so that when we come discuss them next time, we'll be very fast. I think I forgot to tell them to classify the anti-Parkinsonism, but they're also not many, so they're also easy to go through. So do we have any? If you have no questions, then you can sign in. I think we'll be able to continue next week. When are we having our cart? We need to start thinking of the first cart.